Hi there and welcome to tutorial 4 on the Edexcel S2 A-level module, and this is on the continuous uniform distribution. For further help with your studies, do check out youtube.com/MrArnold'sMaths, and please do follow me at Mr. Arnold's Maths on Twitter. Okay, so a continuous uniform distribution, sometimes called a rectangular distribution. And that's where the it's a little bit like the discrete uniform distribution from S1, where the probability remains constant across the whole thing. So if the probability remains constant over the interval between A and B, remembering that the total probability beneath this rectangle must be equal to 1. Well, the area of the rectangle must be calculated by doing the length times the width, and the length in this case will be b minus a. And in order to make the height, or the area of this whole rectangle equal 1, this height is going to have to be 1 over b minus a, because 1 over b minus a multiplied by b minus a will equal 1. So, and that's the definition of a continuous uniform distribution. So it has a probability density function of 1 over b minus a between a and b, and 0 otherwise. So let's have a quick look at an example. So we've got the continuous random variable x. It's got a PDF as shown in the diagram. First of all, we need to find the value of k. And what we have to remember is that the width times the height of the rectangle must equal 1. So k minus 2.6 multiplied by 0.1 must equal 1. So what I'm going to do is I'm going to divide both sides by 0.1. So we get k minus 2.6 equals 1 divided by 0.1 is 10. And then adding 2.6 to both sides, k equals 12.6. So fairly straightforward there for the first part. Let's have a look at the second part. I need to find the probability that x is between 7.9 and 4. Well, the first thing I'm going to do is work out the width of this interval. So 7.9 take away 4. Let me make that 7.9 and not 7.6. 7.9. 7.9 take away 4 gives me 3.9. And if I do 3.9 multiplied by the height, which is 0.1, that will give me the area under the curve. And 3.9 times 0.1 will give me 0.39. So a fairly straightforward example there. Remembering that the area under the curve is the probability. And it's quite handy when our shape is a rectangle. Okay, so we've got a second example here. Continuous random variable x has a uniform distribution over the interval 2, 8. That's what this notation means. And I need to write down the distribution of y equals 2x plus 5. So I just need to transform the interval. So when x equals 2, that means y will equal 2 times 2 plus 5, which gives us 9. And then when x is equal to 8, that gives us y equals 2 times 8 plus 5, which is going to give us 2 times 8 is 16, 16 and 5 is 21. So what we can say is y is going to be a uniform distribution over the interval 9, 21. So between 9 and 21. Okay, next part of the question, find the probability that that y is between 12 and 20. So let's just write down the probability density function for, well, not f of x, let's do f of little y. So f of y is going to be equal to, and remember it's 1 over b minus a, so 1 over b, which is 21, a is 9, so 1 over 12, when y is between 9 and 21, and then it's going to be 0 otherwise. So all I need to do is do the height of the bar. The height of the bar in this case must be 8. The width of the interval between 12 and 20 is 8. So I need to do 8 multiplied by 1 over 12, which is going to give me 8 over 12, which is 2 over 3. So that is the probability that y is between 12 and 20. Okay, next we're going to move on to the mean and the variance, and it's important that you know how to actually derive these. So this is something that needs to be learnt from scratch. So we're going to derive the expected value of x, or the mean of x, for a a continuous uniform distribution. So we should remember that mu, or the expected value of x, equals the integral over all possible values of x times f of x dx. And when f of x for a discrete uniform distribution, or a continuous uniform distribution, f of x for a continuous uniform distribution is 1 over b minus a between a and b, and 0 otherwise. So what I need to do is, we need to do the integral between a and b of x times 1 over b minus a, because f of x is 1 over b minus a, and do that with respect to x. Now 1 over b minus a is going to be a constant, so what I can do is I can actually factor that outside. So I'm going to do 1 over b minus a, and integrating x dx, I'm going to get a half x squared. I need to evaluate that between a and b. So that's going to be 1 over b minus a, into putting b in, I'm going to get a half b squared, and then putting a in, minus half a squared. And I'm going to factor out this half. So I get 1 over 2 times b minus a into b squared minus a squared. Let's just scroll down a little bit. Now, b squared minus a squared we should recognize as the difference of two squares. So essentially what I have is b minus a times b plus a all over 2 times b minus a. And what we can do is we can cancel out the b minus a above and below. So the mean, or the expected value of x, for a discrete uniform, or a continuous uniform distribution, is going to be b plus a over 2. And that's it. And we do need to understand this proof for the exam. Okay, let's have a look at the variance now. So I need to prove what the variance is. Now we should remember that the variance of a discrete random variable, x, equals the expected value of x squared minus the expected value of x squared. In other words, the mean of the squares minus the square of the mean. And hopefully we remember from before as well that the mean of the squares, or the expected value of x squared, is given by the integral over all possible values of x squared f of x dx. So what we're going to do now is we're going to integrate between a and b of x squared times, and f of x again is 1 over b minus a. Just to tell you, this is not the proof they have in the book, but I do prefer this one. So again, 1 over b minus a is going to be constant, so I can factor that out. 1 over b minus a is constant. So it's 1 over b minus a into 1/3 x cubed, because I'm integrating x squared, 1/3 x cubed, evaluated between a and b. So we get 1 over b minus a times, putting b in, we get 1/3 x, or not 1/3 x, 1/3 b cubed, 1/3 b cubed minus 1/3 a cubed. And just like before, we're going to factor out. We're going to factor out 1/3. So I get 1 over 3 times b minus a. And that's times by b cubed minus a cubed. Now this, b cubed minus a cubed, is the difference of two cubes. And the difference of two cubes can be written as b minus a times b squared plus ab plus a squared. Okay, now we should be able to notice that above and below the line we can cancel out the b minus a. So b minus a cancels out with b minus a, and we get left with b squared plus ab plus a squared all over 3. Now that's the expected value of x squared. So I need to now write, so we got the expected value of x squared minus, I need to take away the expected value of x to be squared. So the expected value of x squared is b squared plus ab plus a squared all over 3 minus, and the expected value of x is b plus a over 2. So we should remember that from previous. So b plus a all over 2, and that needs to be squared. Okay, so we get b squared plus ab plus a squared all over 3 minus, and then squaring this out, we're going to get b squared plus 2ab plus a squared all over 4. Okay, our common denominator here is going to be 12. So, common denominator here 12. So I need to do 4 times all of this. So I get 4b squared plus 4ab plus 4a squared. And I need to do 3 times all of this, minus 3b squared minus 6ab minus 3a squared. Okay, let's gather together all of this. We got 4b squared minus 3b squared, which is b squared. 4ab minus 6ab is minus 2ab. And then 4a squared minus 3a squared is plus a squared. And that's all over 12. And then there's one final little thing we can do. B squared minus 2ab plus a squared actually factorizes to b minus a to be squared. b minus a times b minus a will give me this. So it's b minus a all squared over 12. And that's the result. So that is the variance for a continuous uniform distribution. Okay, so let's look at the cumulative distribution function for the continuous uniform distribution. So we've just got to remember that the probability density function is 1 over b minus a when x is between a and b, and it's 0 otherwise. So the cumulative, so I would like to know, suppose that's b there and that's a, and call this x. If I want to know the probability up as far as x, what I need to do is I need to integrate 1 over b minus a dx between a and x. So, well, 1 over b minus a can be factored out. So I get 1 over b minus a evaluated, and the integral of dx is x, so evaluated between a and x. So I get x over, or x minus a, should I say, right, 1 over b minus a times x minus a, and then expanding that out, or multiplying the x minus a times the 1, we get x minus a over b minus a is going to be the function. So f of x is going to be 0 when x is less than a. It's going to be x minus a over b minus a when x is between a and b, and it's going to be 1 otherwise. Not otherwise, or when x is greater than b. When x is greater than b. Okay. Alright, some examples. So, in a computer game, an alien appears every 2 seconds. The player stops the alien by pressing a key. The object of the game is to stop the alien as soon as it appears, given that the player actually presses the key t seconds after the alien first appears. A simple model of the game assumes that t is continuous uniform random variable defined over the interval 0 and 1. So I'm asked to write down the probability that t is less than 0.2. So let's just write that. T is a continuous uniform random variable over the interval 0 and 1. So we have to think about this. That means that f of t must equal 1 over b minus a, which is 1 over 1, which is 1, and 0 otherwise. So between 0 less than or equal to t less than or equal to 1, I should be using little t here. So between 0 and 1, the probability must be equal to 1, and it's 0 otherwise. Okay, the probability that t is less than 0.2 must equal, well, the distance between 0 and 0.2 times by 1, which is 0.2 times by 1, which is 0.2. The expected value of t, by symmetry must equal a half, must equal 0.5. And just to kind of clarify where I got that from, if we were drawing the axis, and if I put my rectangle in here, so we know it's defined between 0 and 1, and the height must also be 1. By symmetry, the expected value of t must be a half. And then the last part says use integration to find the variance of t. Well, that means we're going to do the integral between 0 and 1 of t squared dt, so that's the mean of the squares, minus the square of the mean, so minus a half squared, and the integral of t squared dt is going to be 1 over 3 t cubed evaluated between 0 and 1 minus a half squared, which is a quarter, so we get 1/3 minus a quarter, and 1/3 minus a quarter is 1 over 12. Okay, another example. A child has a pair of scissors and a piece of string 20 centimeters long, which has a mark on one end. The child cuts the string at a randomly chosen point into two pieces. Let x represent the length of the piece of string with the mark on it. So, what we have to think is, it could be equally likely to be any distance from the mark. So it follows a continuous uniform distribution. And it could be right on the mark, or it could be up as far as 20 centimeters from it. So that's the interval it follows, which means that f of x is probably 1 over b minus a is going to give me 1 over 20 when a less than or equal to x less than or equal to b. Or in this case, well, that's 0 less than or equal to x less than or equal to 20. And it's 0 otherwise. Okay, write down the name of the probability distribution of x. We've done that. Sketch the graph of its probability density function. Okay, let's do this as quickly as we can. So, okay, now it's going to be a rectangular distribution between 0 and 20, and for the total area under the graph to be equal to 1, this must be the height of the graph must be equal 1 over 20, and that's f of x, and that's x. Okay, find the values of the expected value of x. Well, the expected value of x by symmetry is quite clearly 10. And if you didn't remember, well, it's the formula, isn't it? It's b plus a over 2, and 20 plus 0 divided by 2 is 10. And the variance of x, we derived that earlier on. It's b plus a, where are we? Here. B minus a all squared over 12. B minus a all squared over 12. Which is going to give me 20 minus 0 all squared over 12. So I get 20 squared over 12, which is 400 over 12. And then 400 over 12 is 33 and 1/3. And the final part, using your model, calculate the probability the shorter piece is at least 8 centimeters long. Well, if it's at least 8 centimeters long and it's the shorter piece, that means at most it could be 10 centimeters. So I want the probability that it's between 8 and 10 centimeters. So I'm going to work out f of 10 and take away f of 8. Well, f of 10 is x minus a over b minus a, which is going to give me 10 minus 0 over 20, minus f of 8, which will give me 8 over 20, which is a half, minus 8 over 20, which is 4 over 10, which is 2 over 5. Okay, That's 5/10, that's 4/10, which leaves me with a probability of 1/10. Alright, one more example to go. Joan records the temperature every day, and the highest temperature she recorded was 29 degrees, the nearest degree. Let x represent the error in the measured temperature. Now we tend to use the continuous uniform distribution for errors a lot. Suggest a suitable model for the distribution of x. Well, it would make sense if x is the error, so x is uniformly distributed. And the error, well, you could be off by minus 0.5 because it was recorded to the nearest degree, or you could be over by 0.5. So you could be below by half a degree or above by half a degree. So that is part A. Part B, using your model, calculate the probability that the error will be less than 0.2 degrees. So what I want is the error has to be less than 0.2 degrees. So I want the probability that it's between 0.2 and, sorry, minus 0.2 and 0.2. Now, in order to do that, we need to work out the model. So f of x 1 is going to be 1 when it's between minus 0.5 and 0.5 and 0 elsewhere. Now, if we think about it, the width of this interval goes from minus 0.2 to 0.2, which means it's going to be a width of 0.4. The height is 1, so 0.4 times 1 gives us 0.4. And then find the variance of the error in the measured temperature. The variance of the error. Well, the variance is going to be b minus a squared over 12, which is going to be 1. B minus a is 1 squared over 12, which is 1. So that's part B there. Part B here, and then part C, quite straightforward to work out. I think we've got one more example to go, so let's do this last example before we wrap it up. Jamil catches a bus to work every morning. According to the timetable, the bus is due at 9 AM, but Jamil knows that the bus can arrive at a random time between 3 minutes early and 10 minutes late. The random variable x represents the time in minutes after 9 AM when the bus arrives. Suggest a suitable model for the distribution of x and specify it fully. Again, we're assuming that it's equally likely to arrive 3 minutes early as it is 10 minutes after. So it would follow a continuous uniform distribution. So x has a continuous uniform distribution. Now it could arrive 3 minutes late or up to 10 minutes after. Which means that f of x has a PDF of 1 over 13 when minus 3, or when x is between minus 3 and 10, and 0 otherwise. Calculate the mean value of x. Well, mu, or the expected value of x, equals b minus b plus a or b minus a over 2, which is going to give me, I'm losing the run of myself here, let's just go back and check this. The mean is b plus a over 2, so let's just make sure we're doing this right. B plus a over 2, that's b plus a over 2 is going to give me 7 over 2, and 7 over 2 is 3.5. Okay, that's the mean. Find the cumulative distribution function of x. So the cumulative distribution function of x. Now, remembering that f of x for a continuous uniform distribution is going to be 0 when x is less than a, it's going to be x minus a over b minus a between a and b, and it's going to be 1 when x is bigger than b. So we can just use that information here again. F of x for this particular function is going to be 0 when x is less than minus 3. It's going to be x minus 3, which is x plus 3, over 10 minus 3, which is 13, when it's between minus 3 and 10. And finally it must be 1 when x is bigger than 10. And then finally it says here that Jamil will be late for work if the bus arrives after 9:05 AM. So I want the probability if it's after 9:05, so any time after 9:05. Now it could arrive between 5 and 10 minutes late, which means the width of the bar is equal to 5. So we're going to do 5 times the height of the bar, which is 1 over 13. 5 times 1 over 13, which will give me 5 over 13. Okay, try to keep that one as short as I could. Hopefully you found it useful. I'll be back again soon with another video, so best of luck with the revision, and I'll talk to you again sometime.